so. All right, we're going to get started shortly. Our first 3 presentations are all going to be remote. No, the third one is as well. It doesn't say there, but it is. Those of you that are remote, I will verbally give you your 2-minute warning. So I apologize in advance that I'll be interrupting you while you're speaking to do that. But there's sort of the easiest way to communicate that. We'll go ahead and give people a couple more minutes to filter in. Thank you. All right, thank you all for being on time. We will go ahead and get started. Our first speaker of the session is Alan Dressler. And Alan, go ahead whenever you're ready.
First, a minute of introduction, sort of history and motivation. 30 years ago, Aura sponsored a study of what might follow the Hubble Space Telescope, especially important if its planned repair was unsuccessful. Soon after, HST was restored with spectacular results and unprecedented public enthusiasm. HST's early work on distant galaxies inspired the HST and Beyond Committee to recommend to NASA an Origins program, recognizing this once-in-a-civilization opportunity to look back to the birth of the first stars and galaxies. In this key cosmic event, production of the first heavy chemical elements and galaxy reservoirs, the universe took a sharp right turn from heat death oblivion to a future of fantastic complexity, to planets, to life. Our origins lay in that epoch. HST could take us close to this, but to reach the beginning, a large cryogenic space telescope was needed. That was the principal recommendation of HST and Beyond. Its prime mission, as I like to think about it, to make the first measurements of the growth via star formation of newborn galaxies. 30 years later, at my age, I am fortunate to be one of the astronomers pursuing that mission. Measuring the history of star formation in galaxies has frustrated astronomers since Walter Baade discovered 2 populations, old and young, in M31. Baade was successful because his Mount Wilson plates resolved individual stars in Andromeda. The challenge is trying to extract histories from integrated light where the stellar populations of different ages are together. It should be easy. For every generation of stars, there is a spectral energy distribution, SED, that shows its age and evolves as the population ages. And you see here on the left-hand side, stellar population templates, SEDs, showing what the energy distribution looks like from different age stars. But look closely and you'll see the problem. The SED evolves rapidly from 1 megayear to 10 megayear through 100 megayears, then more slowly up to 1 gigayear, and then 2, and after that, all SEDs essentially look the same. As an example, Kelson, Abramson, and I use this rapid evolution of stellar populations less than 2 billion years. Study star formation histories for the previous billion years for redshift 0.5 galaxies. And in this study, we found that 25% of Milky Way mass galaxies form more than half their stellar mass after redshift 1. Surprising. Still, we could say nothing about how rapidly these galaxies grew from their births to redshift 1. If it's so hard to study star formation histories today or back at redshift 1, how can we hope to carry out the prime mission of JWST, watching galaxies grow through their first generations of stars? Here's the good news. Finally, this is easy. From redshift 15 to 5 is a billion years, the first billion years of cosmic history. So the light is dominated by main sequence A stars whose lifetime is 1 billion years. Perfect. So no longer will we have to worry about older populations that all follow essentially the same giant branch, which makes them all look alike. Now we have stellar energy distributions, SEDs, that are distinguished by their ages. So I wrote a program called SED-Z-Star, Fortran code, to combine these stellar population templates over this period, redshift 5 to 12, say, to find the best fit to an observed SED. I like to think of these spectral templates not as vectors, which they are, but like chords. They are 7 notes over 2+ octaves, and all the templates are playing the same notes, but not the same loudness. So there's a difference of emphasis across the chord. So here are some templates for these A stars. This is template growth from redshift 12. Here's a redshift 12 population, 11, 10, 9, 8, 7. My point is that they're all quite different. They're non-conformal, which means you could reasonably hope to separate out one from another. So SED-Z-Star uses stellar population templates that start at redshift 12, set that start at 11 and 10, all recording the SED's evolution observed to a later epoch. And we use that to match galaxy fluxes from deep near-cam imaging, 7 bands from 1 to 5 microns. The templates include expected nebular mission and non-thermal continuum star-forming population. So the first data I had for this came from the ERO program GLASS, and I was able to get spectra for SEDs for 24 galaxies, a very small sample, but one that was enough to theory the program. So I just showing you this from that paper to show you how the format of the output of SED-Z-Star. The middle panel shows you the data points, the near-cam fluxes with their error bars, and this magenta band shows you the quartile range of 21 solutions that the program found for this SED. And it found that by invoking star formation at these various epochs that you can see here, running from 10 to the 9th to 10 to the 8th solar masses per epoch. That's the amount that's being added. And over here you can see the run of chi-squared. And for this galaxy, the best fit occurred at redshift 6.6. So using that just to sort of show you graphically how the program works, you start with a population of stars born at redshift 12, and you say, how can I fit the observed data? And you look here and you see, oops. The answer is no, it's a terrible fit, and that's not surprising because there would be all these dropout points if that was in fact where the light was coming from. Go back there, and then next, you add 11, observe the galaxy at redshift 11. You go down, in this case it skips 10 to 9, and you see the SED is getting, the fit is getting better. Finally, all the way down to redshift 6, which is where the chi-square bottoms out, and that's the fit that you get. It's very noisy data, and so I was thrilled just to see that I could get anything at all at this point. But it showed how you could, I'm just trying to show you how the program. So now I'm going to go on to the second paper because the examples are so much cleaner from the JWST deep fields. So here are the 4 types of star formation histories that were found in the first paper. The first one requires only one template, redshift 7, star formation about 10 to the 8th, to describe the SED. And you can see this purple line, it does it quite well. Just like in the early study, I found that almost half of the SEDs, the data, looked like this. It was surprising. Do they all look like no? No, not at all. Here's one over here where 2 epochs of star formation explain the shape of the CCD. One at redshift 10, about 10 to the 9 solar masses, one at 2 times 10 to the 8th at redshift 7 with a separation of about 600 million years. You can see the contributions that each of these star formation epochs has and how it fits the data very well. There are also what I call 3 epoch contiguous star formation histories are very prominent at the end of the epoch, and they actually last for about 500 million years because the epochs are longer there. And then finally, there's some very long star formation histories that start at the beginning of the epoch and go all the way to the end, which I just described as contiguous. And I just want to make a mention that if you see gaps like that, that's nothing to be too excited about because the non-negative least squares program cannot put in negative star formation, so it's one of its characteristics. But if you see a big gap like that, that certainly is significant. So this paper that is reporting all of this has about 900 galaxies. It's the good south deep field. It was done by JWST, 25 square arc minutes. Covers now the whole redshift range, which the first paper did not do. And the final sample of 900 galaxies is split up to these kind of redshifts here, 500, 200, 100, and very small sample above that. And now I'm going to show you just in the redshift 7 range, more examples of the star formation histories. It does this for all those redshift range. 18 examples. So the ones at the top here are the starbursts. You can see they're all quite well fit by a single episode of star formation. Then you have here a double burst of star formation, typically. Here's a little triple. These are these 3 epic star formation histories. And then finally, at the bottom, these things that seem to last the duration of the period from redshift 6 to 12. So you've heard a lot about burstiness and already in terms of explaining what we see as bright galaxies. But now you're actually seeing star formation histories. That's not indirect evidence, but just star formation histories, direct evidence that they are in fact bursty. And here is in fact frequencies of occurrence, as you see. Between the burst and the stochastic, which are multiple bursts, it's like 70% of the population. And I've just plotted them out as a function of redshift here, just to show you that the same types are available. They cover the whole range.
Alan, you have 2 minutes left.
Thank you. And you also see they cover the same mass range, typically between 10 to the 8th and 10 to the 9th. And here's just a sort of a graphic thing from the paper that shows you that the mass that's being generated in this field, in this epoch, is mostly put in by these little steps of star formation histories. So my summary is at this point, the first thorough study of the discrete star formation histories of the first galaxies. First of all, it sort of shows that this works because just the fact that the A star templates make good fits to the data means that we're probably doing something sensible. I didn't mention this, but the lack of rising star formation histories of all the ones I do find that are long are falling suggests me that the very first phase of this star formation has been shorter and obscured by dust. The variety of star formation history, these 4 groups, again, the main result that bursts and double bursts are really the story here. And for future, it's engaging with the theorists, the modelers, and comparing their results with JWST data and observations. Describe the physical processes that drive the star formation histories and constrain the theories and models to test and improve our understanding of the physics. Just throw in So we're doing that now. This is from part of the collaboration with the theoretical community, with FIRE, and then with Andrew Benson, with Galacticus, and you can see some star formation histories that were pulled out of his program that in fact show bursty things, and not only bursty star formation episodes that are about the right amount, but that they die. What is it that's causing these things to shut down, which is what I also see in the data. That's quite interesting. I think that's the major challenge. And I'll stop there. Thank you. Hello?
Any questions? Thank you.
Alan, this is Roger Windhorst. Great talk. Looking forward to your colloquium also on this. For the most actively star-forming objects, how would emission lines affect the SED fits? Is that included? Or
there's detail in the paper, but remember, Roger, as I said, that the templates themselves have the emission for sort of a standard H2 region contribution. So they're in there, and you can actually see them if you put the medium bands. There are two medium bands that often fall on oxygen 3 and alpha. So you could see them when they're in smaller intervals. But for the big bands, that's already been calibrated. But there's a long discussion in the appendix showing lots of examples of the ones I showed you where you don't see any street emission. And some that there are, and it seems to be.
All right, we have time for one more question. All right, are there any questions online? All right, let's thank Alan one more time. And if the next speaker could go ahead and share his screen. All right, our next speaker is James Trussler. James, go ahead when you're ready.
Okay, good afternoon, everyone. I'm James Trussler from the University of Manchester, and I'm so grateful to be able to participate in this very special week. We've really been anticipating, really dreaming of this moment for so long, the first year of James Webb Data, and it's finally upon us now. And just hearing the roundtable discussion this morning, all the different science cases, all the developments that we've been making that are beyond my field that I don't even know about, I found that really exciting, and I can't wait to hear more about it the coming days for this week. So what I want to talk about today is really on one of James Webb's chief science goals, namely first light, and so finding and characterizing the first galaxies in the universe with JWST. So I'll begin by talking about a direct approach, simply put, directly imaging and observing these first galaxies. And specifically, when I refer to first galaxies at this part of the talk, I mean population-free galaxies formed of population-free stars, pure hydrogen, pure helium. And so here's an example of a theoretical spectrum of a population-free galaxy placed at redshift 8 with 10 to the 6 solar masses. And what you can see is this wealth of very strong, bright emission lines. And it's really these strong lines, the presence of these lines, but also the absence of these lines that forms the basis for our selection and identification of population-free galaxy candidates. So I'd just like to go through some of the key defining features in a population-free galaxy spectrum. So the first are the bright recombination lines of hydrogen. Note shown in here the Balmer series H alpha, H beta, but in principle also Lyman alpha. And this comes about because these population-free stars are very massive, they're very, very hot. And so they're very effective at producing ionizing radiation that's capable of ionizing hydrogen gas, which recombines to produce these very bright lines. But not only are the stars hot enough to singly ionize hydrogen, they're also hot enough to doubly ionize helium. And so what that means is that this doubly ionized helium gas, it too can recombine, producing helium-2 recombination lines, both in the rest frame UV on the left, the helium-2 1640 line, which I'll be discussing in detail in this talk, and also in the rest frame optical shown in the middle, the helium-2 4686 line. And finally, because these population-free galaxies are pristine, they contain no metals, unlike their metal-enriched counterparts, they have no metal lines, like these bright O3 lines or these bright neon-free O2 lines. And so these free defining features, the strong hydrogen recombination, the strong helium-2 combination, and the lack of metal lines forms the foundation for a selection of population-free galaxy candidates with the James Webb data. And so I'd just like to begin by outlining one of our selection procedures. It's a color selection. And so for a galaxy at redshift 8, its characteristically strong H-alpha emission resides within the MIRI F560W filter. And as you can see, the bandpass average flux density, shown by the red data point, is boosted beyond the continuum level shown in blue. And so that is one key aspect of this color selection. The other aspect is the lack of metal line emission, the lack of characteristically bright O3 emission in the NIRCam F444W filter for a redshift 8 galaxy. And so combined together, that lack of oxygen-free emission at the bottom and the enhancement of H-alpha emission at the top drives characteristically red colors to the point pushing these pop-free galaxy candidates towards the top of this diagram. Now similarly, we also have S3. This is the near-infrared, perhaps less well-known counterpart to the oxygen-free doublet. So it also serves as a basis for metal line emission. And so these population-free galaxies will also lack this S3 emission in the MIRI F770W filter. So if you combine, again, the strong H-alpha on the left and the lack of S3 metal line emission on the right, you get characteristically blue colors for these population-free galaxies on the horizontal axis. So combined together, you get this color selection diagram. And there's a lot of information here, but I'll just guide you through the most important parts. So what we show here is the initial colors and the subsequent tracks, the evolution of cosmic time of these different colors in this color plane. The population-free galaxies for different IMFs are shown in blue. I'll discuss the different IMFs more in detail in a bit. And all the non-population-free models, so the middle-enriched galaxies, are shown in the non-blue colors. So the green, the yellow, the orange, and the red, going from 2% solar all the way up to solar metallicity. So the key point is that the population-free galaxies immediately after starburst, that's the plus symbols that you see, occupy a unique region within this color plane, in the top left region, for precisely the reason that I mentioned before. The strong H-alpha and lack of O3 pushing them towards the top, the strong H-alpha, the lack of S3 pushing them to the left. And so if we see galaxies in our NIRCam and MIRI searches that occupy this region within this color diagram, we have good reason to believe that they are population-free galaxy candidates, or at the very least, very metal poor. So that's all great, but that's not really the end of the story, because this approach uses a combination of NIRCam and MIRI, specifically the MIRI for targeting that H-alpha emission and that S3 emission at redshift 8. Now, MIRI is an absolutely fantastic instrument, far exceeding what we could do prior to James Webb in the Spitzer era. But it is true that compared to NIRCam, it is quite a bit less sensitive. So what NIRCam can detect in 1 hour, it takes MIRI 50 hours. But that's not quite the full story, because NIRCam also has a wider field of view in the sky, roughly 4 times that of MIRI. So if you put that together, what NIRCam can survey and detect in 1 hour will take MIRI 200 hours. And so what we really need, if we want to push this pop research with MIRI, we really need to leverage on the flux boost from gravitational lensing, doing deep MIRI imaging on these galaxy clusters, pushing that in future cycles to make such detections possible within relatively short exposure times that we can survey many clusters in these observation programs. So instead of just having to leverage on gravitational lensing, we also seek an alternative approach for finding population-free galaxy candidates. And this is leveraging on that other key defining characteristic of population-free galaxies, namely their very strong helium-2 recombination line emission, particularly the 1640 line in the Rastram UV. Now, this line is characteristically very strong for population-free galaxies, and so we can search for the imprint that it leaves on photometry, but not on wideband photometry, but specifically on medium-band photometry. Because yes, it is true that this line emission is characteristically strong for POP3, but that's actually in a relative sense. In an absolute sense, the line equivalent widths are actually quite small, something between 10 to 100 angstrom rest frame, depending on your POP3 model. So we need medium band imaging to really search for that signature, the imprint that it leaves behind on the medium band photometry. This is something that is very much possible, depending on the POP3 IMF, how top heavy it is. You can look at a signal between 0.15 to 0.3 mags. So certainly something that we can assess within the realms of the James Webb data, requiring a 2 to 20 hour integration time for a 5 sigma detection. Now, once we have our population-free candidates for either method, we want to follow these up spectroscopically to confirm their population-free nature, and specifically to probe that helium-2 1640 line, again, that's characteristically strong, characteristically bright for population-free galaxies. And the equivalent width of that line, how bright it is compared to the continuum level, is what I'm showing here on the vertical axis as a function of age after the starburst. And the main point I want to make is that the population-free models, the different IMFs in blue, are orders of magnitude larger than the metal-enriched non-pop-free galaxies. So it's very, very clear if you saw such a strong helium-2 of equivalent width that we're looking at population-free. And not only that, in principle, it is also possible to distinguish between different pop-free IMFs with these different lines corresponding to the different characteristic mass of stars formed for pop-free star formation, whether it's 100 solar masses, 10 solar masses, or 1 solar mass. Now, within our first year of James Webb data, we've had some interesting discoveries, and particularly when it comes to potential population-free star formation activity. This is in the vicinity of GNZ11. We've seen its spectra before. We've heard about it before. For those that are not familiar, GNZ11 is really one of the brightest galaxies, high redshift galaxies we knew of in the Spitzer-Hubble era. And not only that, it was the highest redshift candidate whose redshift we were rather confident in being around redshift 11. It's been followed up now in the first year James Webb data, both with NIRCam and with NIRSpec. And so if you look in the vicinity right next to GNZ11 on the sky, you see this excess of emission as reported by Roberto Maialino in his 2023 paper, precisely at the wavelength where you'd expect to see the helium-2 1640 line at the redshift of GNZ11. That's shown more clearly in the bottom. Not only that, based off of the lack of a continuum detection in the NIRCam photometry, they inferred that the equivalent width of this line must be very, very high, 170 angstroms, so really pushing the limits of our expectations from our pop-free models. So this definitely merits further follow-up in future cycles, both spectroscopically, of course, but I also want to make a case for follow-up imaging, because in principle, we can verify this emission through the imprint it leaves behind on the medium band imaging I mentioned before. Specifically, the F182M filter for this line at that redshift is where you'd be probing this. And you'd expect to see a photometric excess of 0.65 mag, so a very, very strong signal that we could easily verify with not even that deep follow-up imaging. But not only could this imaging...
James, you have 2 minutes.
Okay, not only can this imaging tell us about whether it's pop-free, but whether the helium-2 line is there, but also whether we're looking at pop-free or Dirac collapsed black holes powering that line emission, because these different sources for that line emission occupy distinct regions in the color plane that I showed before. This comes about from that power law emission that we see for Dirac collapsed black holes at accretion disks. So that was really our direct search for the first galaxies, and now I just want to briefly talk about our indirect search for the first galaxies. And the key principle here is to look for old stars in very high redshift galaxies when the universe was very, very young. Because in that way, you can wind back the cosmic clock even further back beyond the epoch of our observation and learn about the early star formation history in these galaxies. And for this, we've been using the Pulse dataset that Roger Winter spoke about earlier, as well as public datasets including GLASS, NGDeep, and SEERS. So the photometric signal that we see for evolved stars is this Balmer break. It's the sudden shift that you see in the continuum level here as we enter the rest frame UV to the rest frame optical. It's this F444W excess. But we want to make sure that what we're seeing is due to a Balmer break, these intermediate A-type stars, a few hundred mega years old, and not due to the strong line emission. So what we require is that these galaxies are at the right redshift, sufficiently high redshift, that those strong emission lines, O3 H beta, are redshifted out of the F444W filter so that we can attribute it to a Balmer break. And also we're looking for Balmer break candidates, so we want them to exhibit that sudden jump in their photometry, that Balmer break. So in other words, a jump between the two filters straddling the Balmer break. That's that excess that we're seeing on this color plane. And so in this way, we can generate our list of Balmer break candidates, the strict ones using that color criterion in red, the control sample in blue. And what we can see here is the inferred mass-weighted stellar age from fitting the photometry. And what you can see based off of face value, it seems that the Balmer break, our observational proxy for the stellar age on the horizontal, is a good predictor of that mass-weighted stellar age. As you go further to the right, the ages increase as you go up. And indeed, if you take these ages as they are, the mass-weighted age is 75 to 175 megayears at redshift of 10. This implies a mass-weighted formation redshift of 13 to 14. However, if you apply the same analysis at a lower redshift, the redshift of 8, you see that that trend is no longer as clear. There's a lot more scatter involved. And the reason why this is the case is because these objects being at lower redshift, now the NIRCam F444...
So you should wrap up.
Okay, just one moment, I'm almost there. The F44W filter probes that O3 H beta emission, which is providing additional constraints on the current star formation rates in these high redshift galaxies. So the key point is if we want to get the best star formation rates we can, star formation histories, at the frontiers of James Webb, we really need that Miri imaging as well to constrain that star formation. And so just to finalize really the closing picture of why we wish to do this is because we want to reconstruct the star formation histories of these very distant galaxies. And by doing so, we can indirectly infer the onset of star formation in the universe, really complementary to our POP research. But we need that Miri imaging to do that, and we also need very deep continuum spectroscopy with NIRSpec to be able to do that. So that's something we should really push for in future cycles of James Webb. And with that, I will close. Thanks.
All right, we have time for one quick question. Questions online? All right, well, let's thank James one more time. And then the next can go ahead and share their screen.
Okay.
All right, our next speaker is Mauro Stefanon. Mauro, go ahead.
Thanks for giving me this opportunity. So this first year of JWST has brought to us a lot of exciting new results, and perhaps even more questions than we were expecting, as we can clearly see from this figure. By the way, I mean that questions are really great to have. But more into the topic. So perhaps one of the most tantalizing results from JWST, at least for the high redshift community, has been the discovery of unexpectedly large samples of very bright, likely massive galaxies in the first 400 or 500 millions of cosmic time. And the reason why these galaxies were unexpected is that if we just extrapolate results from lower redshift, we were expecting that galaxies would have had a pretty, let's say, constant or non-evolving star formation efficiency, and instead the large numbers of bright massive galaxies that we observe at high redshift are suggesting that perhaps the very early phases of galaxy formation have seen a phase of an enhanced star formation. And it's very difficult, however, to identify high redshift galaxies. There are solid samples, but also it's it's been quite challenging to also for sources which were commonly considered to be solid high redshift sources have then demonstrated to be unfortunately lower redshift interpolants. But these bright star-forming galaxies are probably one of the most massive ISM reservoir in the early universe. And so one way to study this could be to go after their ISM properties. And Rebels, an ALMA large program led by Richard Bowens, was explicitly designed for this purpose. It consists in the follow-up of with ALMA of 40 bright star-forming galaxies identified over 6 square degrees of sky, with the deepest ground-based and by the time was Spitzer IRAC data. These galaxies were selected to have redshift around 7, between 7.5 and 8.5, and this is the sample that I'm going to talk about a bit. The initial analysis of the ALMA data have shown that this galaxy possess really a variety of physical condition or physical processes, with mergers, outflows, individual, very compact morphologies, and also differences between dust emission and C+, so cold gas emission. One thing that you cannot properly see from these images is that the sample was selected using ground-based and Spitzer photometry, which means that both the spatial and spectral resolution for probing the rest frame UV and optical were quite low. So we are talking about a resolution of about 5 and a spatial resolution of about 1 arcsecond. So we have been very fortunate in obtaining in getting the possibility to follow up 12 of the rebel sources with JWST, and in particular with the NIRSpec IFU capability with the lowest resolution. Here you can see a summary of the main properties for the sample in orange on the right side, and the sample that we are following up is reasonably well describing the average properties of the full rebel sample. And so data are coming in, started to come in last month and or last couple of months. So I'm only going to present you some preliminary results. And here I'm showing you the image stems based on the at the rest frame UV wavelength for 2 of the sources for which we got data, and we can already see that the 2 sources differ quite substantially in morphology. One is clumpy, and the other one is much more compact. But this is the kind of information that sort of we could have already had from let's say HST. The resolution is more or less the same. What gives us JWST, in particular the IFU, is that we can not only study rest frame UV, but also the properties of the light emitted throughout all the most of the rest frame optical, up to about H alpha. And we can already see that not only sources differ one from each other, but also there are significant differences in the emission depending on the wavelength. For instance, here O3 is very different from the rest frame optical. So older stellar population probably occupy or were generated at different location than newer stars. One of the first questions one could ask is about dust emission. So we have dust measurements from JWST, and we have H alpha and also H beta from JWST. And so we could reconstruct dust maps using the Balmer decrement, which are shown here for the 2 sources. As we can see, one source shows quite a clear gradient on the left, and the other source instead is more homogeneous or more noisy. And what happens if we want to compare these Balmer decrement maps to what our information from ALMA? Here it is shown. So for one source, we have a clear detection, which overlaps quite nicely with the peak of extinction from the Balmer decrement, while in the other case, we didn't have an ALMA detection down to the same sensitivities, And so this already, I think, it's a very, very nice result, which shows already even more the variety of physical processes which may undergoing at this high redshift. Another interesting question is about the age of this galaxy. So we can look at, for instance, the specific star formation rate, which is more or less the inverse of the age, and we can compute, we can measure, we can create maps of specific star formation rate, for instance, by taking the ratio between the emission in the H alpha, so the most recent star formation, and the rest frame optical, so more evolved stars. And you can see the results here. And again, we can see, for instance, on the left, that there is a clear trend, or at least dichotomy in the light distribution. And we can see, for instance, that at the bottom right of the source, there must be a quite recent burst, while at the opposite side, the opposite side probably is harboring much more evolved stellar population. And yes, so these maps have been generated after correcting for dust using the Balmer decrement that I've shown you before. So another interesting topic, I think, that has arisen in this year is the existence of galaxies at high redshift with quite evolved stellar populations, as also the talk by the colleague before presented. And so one consequence that we could expect from evolved stellar population could be a higher metallicities. However, so far measurements of metallicities have focused more on lower mass galaxies, and have indicated that low mass or intermediate mass galaxies at high redshift have low metallicity, are quite metal poor. Here we have a nice sample of massive bright galaxies in the epoch of reionization, so it could be interesting to look at the metallicities of these objects. And here you can see at the bottom.
You have 2 minutes.
Thank you. At the bottom, you can see the spectrum that we extracted for one of the two sources, the compact one, considering the full footprint that you can see indicated here with the red line. So the spectrum looks nice. We can measure oxygen abundance. And one interesting thing that I would like to point your attention to is that we can even start seeing here indication of sulfur-2 lines. So even qualitatively, we can see that probably this galaxy is metal rich. And indeed, this is then confirmed by measurements, different measurements. You can see here the full table with the different measurements of metallicity, and we end up with quite high metallicity. How high? It's basically subsolar metallicity, as you can see from the two set of points here. The two sets just refer to two different measurements, and these are significantly higher, significantly more metal rich than let's say current measurements on lower mass galaxies at similar redshifts. And as a very last slide, we can already also start to probe gradients in metallicity. So again, trace star formation histories based on metal enrichment, and this is one example, R23 in this case. Again, here dust corrected using Calzetti and the Balmer decrement that I've shown you before. So this is a first let's say a spatial map of metal enrichment for these galaxies. And I'm leaving here my summary and conclusion, and I'll take questions. Thank you.
Right, we have time for some questions.
Hi, Mara. Great talk. This is Hao Jingyan.
Hi.
I have a question. Probably you don't have a answer right now, but I just wanted to know whether you have a correlation between the metallicity that you derived and the extinction you observed.
Oh, yes, that's a great question. I looked into this for one of the sources. It was this one, because of course I was worried. As you said, you can have correlation, and so your metallicity measurements, the resolved metallicity map could just be dust extinction. And if you do not correct for the Balmer decrement, the metallicity map looks very much like this Balmer decrement map. But once you take into account the Balmer decrement, then you recover this structure, let's say this emission. You can still see here some, let's say, metal enrichment, which overlaps with the location of the peak emission from the dust. But I think this at this point also makes sense. I mean, we expect dust is sort of the other side of metal, so I think after correction, after correction for dust extinction, one would still expect some metallicity at the location of dust. Yeah. But I only looked at this source in detail, well, in slightly more detail, but I haven't looked for the other ones.
We have time for one more quick question.
Thank you for such a beautiful talk. This is Elizabeth Tarantino at Space Telescope, and I'm wondering if you see any differences between the star formation rates derived through the C+ line from the ALMA data and the JWST derived star formation rates.
Oh, this is a great question. We haven't looked into that yet. We are in the process, actually. Yes, that's indeed a great topic, great question. So the C+ is there are indications that C+ is a star formation indicator which is not sensitive to dust, right? And so that gives us the total star formation rates of galaxies. While here we have the possibility to correct, let's say if we start from H alpha or whatever line, we have the possibility to correct for dust emission. And so we can, in principle, compare the two. One thing that we will need to take into account is that the beam size of ALMA is broader than that of JWST. So the emission from C+ comes from, well, sorry, it's not because of the broader beam, but the emission from C+ also comes from a much more extended region. So if you account for that, you probably get higher star formation rates than from just H alpha, let's say dust corrected H alpha. And then the second thing is concerned this time, yes, with the beam. If we want to have a better understanding of the relationship between C+ and let's say rest frame optical, we probably need higher resolution ALMA data because so the beam size in this case for ALMA is about 1 arc second, 1.2 arc seconds. We have high resolution for very few objects. One is already at home. One observation for one object are already fully taken, and then I think we have 2 or 3 more which are coming in. And so, yeah, well, in general, stay tuned because I think this sample is going to produce very nice, interesting results, at least to generate new questions.
Thank you, Mauro. Let's thank Mauro one more time.
Thank you.
Mara, if you could, yeah, thank you.
Yeah. Okay.
All right. Our next speaker is Duncan Austin. Go ahead, Duncan.
Hello, everyone. Thank you very much for having me present my work on UV continuum slopes from combined PEARLS GTO and public JWST near-cam imaging. I'm currently working at University of Manchester with Chris Consulis, and I'm part of the PEARLS GTO team. A lot of the imaging you've already seen from Roger's talk earlier. Okay, so in this talk, I will go over an overview of our current epochs high redshift galaxy sample, as well as highlights from Austin et al. 2023 from NG-Deep, which is now accepted in AppJL. I will then talk about calculating UV continuum slopes and the identification of ultra blue potential Lyman continuum leaking candidate galaxies. Then I will look at the buildup of galactic dust using beta slopes and the Calzetti 2000 dust attenuation law. So I think you've already seen some of this data, especially the one in the top right from Roger's talk earlier, but these are the fields from PEARLS that we use, down to 0.9 microns and up to 4.4 microns of wavelength coverage. So in the top left is El Gordo, and we used just a blank field from El Gordo because we do not consider any of the magnification in our fields. We then use MAXO 416, so the three parallel fields, there two in the bottom left and one in the top right. We use the Clio cluster, blank module, but we don't show that there. And then we also use all four spokes of the NEP field, which is mosaic together in the bottom right. We also use public GTO, GEO, and ERS data, including NG-Deep, SMAX 0723, GLASS, and SEERS here in the bottom left. I think you've seen these first four pointings of SEERS from Michaela's talk earlier, but in epochs we use all 10 pointings and not just the four that are shown there. So in NG-Deep and SEERS, as well as the NEP field, we also use HST ACS data so that we can gain valuable access to the optical data that we need to confirm redshift 6.5 and above galaxies. Okay, so we measure down to magnitudes of around 28.7 to 30.3, depending on the field. That is in the 277W filter. And we find a total of 800 redshift greater than 6.5, Lyman break galaxies over approximately 164 square arc minutes of unmasked data. We calculate photo-Z's using EASY and the Larson 2022 template set, which goes bluer than what the default FSPS template set does. And we also find stellar masses using the Bagpipes Bayesian SED fitting code written by Adam Connell. We do force photometry in 0.32 arcsecond diameter apertures, and we enforce a 10% minimum error, as well as selecting from a stack on the long wavelength near-cam bands of 277, 356, and 444W. We also find 17 brown dwarfs, and we exclude these from our sample using the Sonoro 2018 templates. These are around between 1,500 and about 2,000 Kelvin in temperature, so quite bright. So for more details, see an IMPREP Consulis et al. 2023 paper, where we'll go over more details about our selection process. As a preliminary sort of star formation rate density, preliminary as in it doesn't use all of the fields that we use in this work now, You can see UVLF from the recent Adams 2023 paper, as well as our star formation rate density, which is relatively conservative. So highlights from NG Deep and the epoch sample. So we find this redshift 15.8 galaxy in the bottom left here. And we find this redshift 15.8. So in the orange, we show the high redshift solution here, and in the blue, we limit it to redshift 6 or lower to find an appropriate low redshift solution. And we see that the high redshift solution definitely matches this photometry better. As well as this, we also match to HST dropouts in the Hubble Ultra Deep Field Parallel 2 by Wilkins et al., Burns et al., and McClure et al. We find 2 merging galaxy pairs at redshift 8. So those are the 2 SED fits on the right. And this close merger also has 2 more galaxies within 30 arc seconds, meaning that this could potentially be an overdensity or protocluster in the Hubble Ultra Deep Field second parallel field. Now, me and another of Chris Consolis' PhD students, Tom Harvey, have been working on a new package called GalFind. And this should be available when our currently in prep paper is released. And this package goes from the reduced imaging, and it takes that reduced imaging and gives you a sample of galaxies. Now, we see that a lot of the early studies don't have too much overlap in terms of what galaxies people find with the different data reductions and different ways of choosing the samples. So hopefully this package will be able to give people options and make that whole process a lot more easy. So the main focus of this talk really is on UV continuum slopes. So the first question we ask is, why do we bother to measure beta? Why do we study this UV continuum slopes? So first of all, we can say that from this figure from Tachella et al. 2022, we can see that the UV slope, or the observed UV slope, the biggest impact on that is from the dust. So we can see that redder UV slopes, i.e. less negative UV slopes, are dustier galaxies. So from this, we can study the buildup of dust at high redshift. You can also see that if we successfully remove the dust, which we can't easily do because we don't know what the dust attenuation law is at these redshifts, we can see that if you have an intrinsic beta of less than around -3, this can indicate metal poor population 3 stars or galaxies. Now, also from this figure on the right, from Topping et al. 2022, we can see that ultra blue galaxies require high escape fractions and a potential Lyman continuum Lucas. Now, these could potentially be one of the most valuable galaxies that reionize the universe. So how do we calculate these beta slopes? Now, what we do is we shift the photometry to the rest frame UV using a fixed photo Z. And we remove all bands not lying entirely within the rest frame UV of 1250 to 3000 angstrom. And we calculate beta simply by plotting power law slope of f lambda proportional to lambda to the beta. And this is an example from NG Deep Z12A in our recently published paper. Now, if we plot beta against MUV, what we find is 22 redshift 6.5 to 13 ultra blue candidates with beta less than -3. Now, these have got considerable scattered or considerable error, rather because of our 10% minimum error that we apply on the photometry. But we also remove 25 potential contaminants by requiring our MUVs from the best-fitting SED template and from the raw photometry to be within 2 sigma. So a lot of these faint points or faint stars that you see there are those 25 that we remove because simply the SED doesn't fit the rest frame UV well. Yeah, so I'll point out a minor issue that we're having with source extractor and blending at the moment. Because we correct these sources for them being extended, source extractor currently gives them a radius much larger than we expect the actual half-light radius to be. So we correct these up by a bit too much at the moment. So we're currently finding a lot brighter things than what we actually have. So this is preliminary, so we need to correct this. Yeah, so due to this, these results are a bit preliminary because we have that blending issue. But what we find here is we plot beta against MUV in various redshift bins, and we plot the evolution of those slopes with redshift in the bottom right. Now, these are a bit all over the place at the moment because of our MUV error, but this is preliminary, and we hope to get this sorted out for our paper. Okay, so we then plot beta against mass, with this mass coming from our bagpipes SED Bayesian fitting using log normal star formation history and the CalZT 2000 dust attenuation law. And we see a clear trend with beta and mass. So in the bottom right is these gradients of our fits plotted against redshift. So to investigate this more, we plot beta against redshift on our various mass bins. And what we find is that at redshift 10, the most massive galaxies already appear to be dusty due to their red beta slopes. So this is most likely to be due to dust formation on short timescales, which is likely to be in supernova of the most massive stars. Now, since the supernova impacts these most massive galaxies, it will also occur in the least massive galaxies. So, but we see that those beta slopes are still blue, meaning that a lot of the dust produced in these supernovas has been pushed out of these low mass galaxies at the earliest times. And this is similar to what is reported in Finkelstein et al. 2012, except we now see this trend at much higher redshifts with JWST, whereas Finkelstein do this, I think, to redshift 7 or so, and we find this effect up to redshift 10. Now, of course, we need to investigate whether this effect is induced by the mass completeness, and we need to investigate that with simulations, but we're currently in the process of doing that. So to conclude, I've introduced the epoch sample of 800 redshift greater than 6.5 Lyman break galaxies across 164 square arc minutes at depths between 28.7 and 30.3. We find 22 candidate Lyman continuum leakers with a robust beta less than -3. We see a decreasing average beta with both redshift and towards fainter MUV, although that caveat with the MUV that needs sorting. And we see evidence of dust production in massive, greater than 10 to the 9 solar mass galaxies at redshift 10, as well as supernova feedback driving dust from less massive galaxies at the same epochs. Thank you.
Questions for again?
Thank you. That was a really interesting talk. I was just wondering if you could comment on how much you expect like emission or absorption features in the UV to affect your estimates of the UV slope, given that in most cases it seems like it's just 2 bands.
Yeah, so here I guess is a plot of, so on the right is the CalZT 1994 filters. And these sort of dashed green lines, I don't know how well you can see them on the right, that bar of the top plot. They're where the emission lines lie. So we hope to calculate beta in the CalZT filters as well, and then compare them. And that's what we'll be doing to see if we've got any biases there. But we haven't done that as of yet. So we could well be influenced by UV emission line contamination, yeah.
Thanks.
Yeah, thanks. Great talk, Doug. Do we have any spectra for those 22 Lyman leakers candidates with the bluest beta? That'd be really interesting.
Simply, I'm not sure yet. I need to look in them in more detail. I also want to look at other trends in there. So, for example, we expect them to have low O3H beta equivalent widths if they really are Lyman continuum leakers. Right. So I need to look at that in more detail. But as far as I know, we don't have spectra, but I do need to look at that, yeah.
All right, and we have one question from online.
This is from Colin Norman, who asks, is there a critical mass at high Z where the dust is expelled?
Yeah, I'm not sure to answer that question. Yeah, I'm not sure about that. But yeah, as you can see, it would lie probably somewhere in the region between this green sample at which masses of 10 to the 8 and this 10 to the 9 sample. So I imagine somewhere in that region, right, 8.5 or something like that.
All right, let's thank our speaker one more time. I'll go ahead and get set up for the next speaker. All right, the next speaker can go ahead and share their screen.
Does this work? All right.
Yes, that works. Thank you. And I'll give you a 2-minute warning verbally.
Perfect. Thank you. All right. So, hi everyone. My name is Kasper Heinz, and so I would first very much like to thank the organizers of this meeting to let me talk a bit about some of the work I've been doing over the last few months, year or so ish, and for giving this talk remotely, as I unfortunately could not be there today. So I'm going to talk a bit about some of the substantial gas reservoirs that we've been detecting around galaxies in the very early universe at redshift above 9 or so. And just to set the stage a bit, so we know that neutral atomic hydrogen is basically the link that that bridges the gap between this diffuse intergalactic gas that we have just after the Big Bang and the epoch of recombination. And from this gas, the galaxy halos, they start to condense, and at some point they can become dense and cool enough to start forming stars. So we really want to know, also we really want to infer the H1 gas mass density, or just the gas mass in these galaxies, to understand how rapidly does this process happen of this infalling gas, and what is the time scale for then for this gas to then form molecules and later on stars and stuff. But as maybe most of you know, that it has been notoriously difficult to detect the H1 emission from these distant galaxies, mostly because the 21 centimeter hyperfine line of the atom is so weak. So it's basically only limited to the very most nearby universe. I believe the current record holder is about redshift 0.5 or so for a single galaxy of detecting this 21 centimeter line. But what we can do instead is that we can look for neutral atomic gas in the Lyman alpha absorption toward bright background sources such as quasars, for example, or gamma burst. So here's shown a nice little cartoon where you can see that you have some kind of bright background quasar, and if that quasar sideline intersects the gaseous halo or even the interstellar medium of some galaxy in the foreground, it will produce a very significant and pronounced damp Lyman alpha absorption feature from the abundant H1 in this galaxy. But we know now that these neutral gas reservoirs, they can extend for several tens of kiloparsec, and even more so at higher redshift, as demonstrated in this simulation by Stern et al. Which means that whenever we see a DLA in these quasar sidelines, and increasingly so at higher redshift, we don't really know at which impact parameter we are probing these galaxies, and which phase is it, the circumgalactic medium, the interstellar medium, and so on. So, for example, if you compare here this white circle in the very center, which is the half-light or half-mass radius of the galaxy, and you can see here these black contours, they are basically tracing where you would pick up a DLA at redshift 5 or so. So you can see you can still find a DLA even several tens of kiloparsec away from this from the galaxy itself. And then there's also the added complication that at redshift above 5 or so, the effect from the Gunn-Peterson effect will effectively remove all flux bluewards of the Lyman alpha emission, which means that it's near impossible to detect any distinct damp Lyman alpha feature from a galaxy, or from a large dense gas in or around a galaxy at these redshifts. What we can do, and we have seen in a very few and very rare cases at the redshifts above or redshift around 3 to 4, is that you will occasionally also see Lyman alpha absorption around star-forming galaxies or in star-forming galaxies. So if you look to the left here, you can see that there is a few cases where you have some Lyman alpha emission with this gray line here, but in the black spectrum, you can see this very weak damped Lyman alpha absorption system. And it seems to only be the case for the very rare cases, at redshift 3, and only typically for the most dusty or for the sources with the highest ionization potentials and so on. There's also, I believe a few months ago, there's also published this paper by Lind et al. That found another galaxy, I believe the most significant to date, the strongest H1 column density absorber to date in a galaxy at redshift 3.98. But that also has these very extreme, so log U parameter of minus 1.34 and a very low stellar mass and a high ionization. But that's the only case, I believe, where you can see, the yet only case where you see the strong H1 absorption and very little Lyman alpha emission in the middle of this trough here. Then that nicely sets the stage for we then started to look for damped Lyman alpha absorption in galaxies at much higher redshift, so redshift above 9, to basically go as far back as we could to start to see this the epoch of galaxy formation. Basically, how can we trace actually the H1 gas reservoirs that are currently infalling and building up these large galaxies? So basically, what we require was that we wanted to see a few emission lines, so at least 2, and here there are clearly 3 and more even. And where we have the full spectral coverage and we have a good signal to noise around the Lyman alpha region, such that we can measure this damping feature. And what we found, if you look at this top left panel, is basically we found a very strong damping profile that's much greater than any of the typical IgM models. So we have shown here curves which assumes a neutral hydrogen fraction of 10% to 100% of the IgM. And none of these IgM models are able to reproduce the large damping that we observe in this case here. And when we look a bit further, we found 2 other cases. So also one, this Max galaxy at redshift 10.17, and also this Sears galaxy, also known as Macy's galaxy at redshift 11.4. And while this is a bit more uncertain, this one certainly also shows this very strong damp Lyman alpha absorption systems. And it seems to be, if not universally common, but certainly a lot more common at these redshift than compared to redshift 3, of course, where it was only the most extreme cases that show this broad damped Lyman alpha feature. And then also, I just want to highlight that again, that this feature cannot be explained by the damping effects from the IgM. And this is nicely shown here by our contour plots when we try to model the neutral IgM fraction with the H1 column density, and you can see that it nicely converges on the column density or the abundance, but we only are able to infer basically a lower bound on the neutral IgM fraction, basically because the large damping feature basically washes out any signal from the IgM due to the strength of the line. And then also just to verify, because most of these analyses were done on the prism spectra from NearSpec, which of course has a much coarser spectral resolution in the blue end. So we just had to verify that this damping we are seeing is not just because of the low spectral resolution. So you can see here on the panel in the left that if you look again at this 10% neutral hydrogen fraction of the IgM, which basically is a step function intrinsically, but when you model or when you broaden that with the instrumental resolution, you get this slight damping feature, and then these effects become less and less severe. So if you look at this DLA feature at 10 to the 22 atoms per cubic centimeter, you can see the effects, while still there, it's certainly less pronounced, this instrumental broadening. So this led us to believe that we are actually seeing these very large H1 column densities in these early galaxies. And then we tried to look into whether these were particular types of galaxies, but they all seem to have more or less similar mass and metallicities, and also this offset from the fundamental metallicity relation. So this was from one of my earlier papers to be published in Nature Astronomy, I believe in a few days or weeks, that show this offset from the local relation. And all these red star symbols here, they all show these young galaxies. Where SED modeling, they basically suggest or indicate that the stellar populations is less than 100 million years old, but this is very much dependent on the exact star formation history we choose to model them. And then what we also looked into was basically to compare this H1 column densities to the metallicity and also this O32 ionization state or ionization parameter of local dwarf galaxies that also show occasionally these very large H1 gas reservoirs. And what we found was basically that while they certainly show larger H1 column density on average than typical galaxies at these redshifts, none of the local galaxies, even the most extreme cases, could not explain or showed several factors of lower H1 column densities than what we observe in these early galaxies, which seems to suggest that there is certainly some kind of evolutionary effect that we are really seeing galaxies deeply embedded in this very early neutral pristine gas that is currently assembling onto the galaxies. And then also this is also nicely highlighted by this figure here, where we show both. Well, first of all, that the DLAs we are observing, they expand the redshift space by almost a factor of 2 of where we can detect and characterize these DLAs, and they're also very much in the upper region of the typical column densities in the optical depth we observe for these H1 gas absorbers. Then the next natural step. So now we have identified 3. Yeah, sorry. The next natural step is now that we have identified 3 prominent cases is to do this on a statistical sample. So basically what we do is just that we look through all the galaxy spectra, publicly available galaxy spectra in the epoch of ionization. We require a signal to rise above 3, and then we know the redshift. And then we look through this Dawn JWST archive, DJ for short. And just to quickly highlight this is basically a community effort that we started in Dawn here in Copenhagen at the Cosmic Dawn Center, where we're basically reducing all the imaging and spectroscopy data so far public from JWST. And you can see here we have more than 1,000 near prism spectra already from redshift 0 to 12 reduced and processed and fully publicly available for anyone to download and analyze. So we basically look through a subset of these spectra. And what we found, if you look at this plot here, is as a function of redshift on the x-axis from redshift 5.8 to 12.3, and then this damped Lyman alpha parameter that we defined for this work, which is basically just the equivalent with. So if you have a large value on the y-axis, it basically means more absorption, and you have a low value or negative value, it means Lyman alpha emission, basically. So we can already start from this figure, try to trace basically the epoch of reionization, where above redshift 780-ish, you mostly see absorption either from the IGM or from the intrinsic to the DLA, intrinsic to the galaxy. And then at redshift below, you start to see more prominent Lyman alpha emission. And then also I want to share one final cool result is we had one galaxy at redshift, slightly lower redshift 5.7 or 5.6, sorry, where we also found a very prominent damped Lyman alpha feature. But we tried to fit it and model this feature, but we could not get it to match at the galaxy redshift. But what we found was that all the solutions seem to point at a lower redshift solution that serendipitously matched a galaxy overdensity at the same redshift as the absorption profile seemed to match best with. So this might suggest that we are basically uncovering the H1 gas mass around a massive proto-galaxy cluster at redshift 5.4, and we are basically seeing early structure formation in progress. And with that, I'll just like to say thank you again. That's it.
Thank you. We have time for one quick question. Questions online? Going once. All right, let's thank our speaker one more time. We'll switch over to the last speaker of the session. Yeah. our last speaker is Andrei Kravstov, and I'll give you a 2-minute warning.
Thank you. Good afternoon, everyone. Thank you for organizers for putting this exciting meeting together and for giving me the last word just before the coffee break on interpretation of UV bright galaxies that we heard so much about. Now, this area seems to be an area of some of the most excitement about JWST results, and I think it's not surprising because studying the dawn of galaxy formation was one of the main goals of JWST. This talk will be theoretical about interpretation of JWST measurements, and so the only JWST image I will show is in this slide in the background from the Sears survey, but I'll show you JWST measurements. And so I wanted to give credit to all the great efforts that went into getting these measurements. Now, it's not just generated excitement in astronomical community, but also in a wider community. Many of you probably have seen such headlines, and I know that it generated quite a bit of anguish. But for a series like me, it's actually great. When I see such headlines, it motivates me a lot. So this was very motivating, and we started thinking about how we can make sense of this data. Of course, we're not the only ones, and as models started to roll in, the headlines started to get a bit more muted, right? The Big Bang is still safe, but galaxies are interesting. Of course, they're interesting. This is the earliest stages of galaxy evolution, something that we've been waiting for years. So I'm going to tell you about our effort to make sense of the measurements of UV bright galaxies at high redshifts. And the model that we're using is a framework that we developed for modeling dwarf galaxies at low redshifts. So we didn't develop this framework for the purpose of matching JWST data. We've been developing it for modeling dwarf galaxies redshift in our nearby universe. And the framework was published last year. It includes all the main processes that, modeling of all the main processes that we think are important for galaxy formation that we learn from detailed models like simulations, as the one shown here in the background of this slide. But simulations inform us what's important in galaxy formation. And that's something that's been ongoing for decades. But we've learned that we can also, by parallel development of analytic models and regulator type models, we learned that we can distill the apparent complexities that simulations show to a relatively small set of differential equations with parameterized terms for various processes, but that work quite well in capturing the essence of galaxy formation. So the specific model, like I said, was developed and published last year for dwarf galaxies. I'm going to break the rule that I use to teach students about giving the talks, and I'm going to show you a slide with a bunch of equations. But the purpose of here is not for you to absorb these equations. You can look at them later if you look at this slide, or if you can look at the paper, but to show that the model is simple enough to fit all of the main equations of the model into a single slide. Okay? These are the differential equations that the model solves. And so it's just a few pages of Python code, and what we call this model is GRUMPY, which stands for Galaxy Formation with Regulator Model in Python. And this is a very forced acronym because we just wanted to call it GRUMPY. We worked on this model in 2020 and 2021. GRUMPY, the cat, passed away in 2020, and also this was our general mood at the time as well. So the model is quite simple, like I said. All the equations are here, and I could have walked through this if I had a couple of minutes more, but I'll refrain from doing this. But despite its simplicity, we actually showed in this paper and also follow-up papers that it reproduces a wide range of properties of nearby dwarfs. Surprisingly so. It worked batter than I would expect such simple model to work. But anything from metallicity luminosity relation, size luminosity relation, the baryonic Tully-Fisher, diversity of star formation histories, the abundance of Milky Way satellites that we looked at in great detail. This model can match all of it without changing parameters, right? All this data is reproduced with the same set of parameters. But of course, this agreement is great, but the good things about theoretical models, it also is where you can identify discrepancies because you can learn something about the physics that's missing in the model. And one area where we saw discrepancy is in the star formation rate stellar mass, so the main sequence of galaxies. The model, which is shown by red points here, does a pretty good job on reproducing the mean trends shown by observed galaxies, shown in blue, but the scatter is much smaller. So the observed galaxies have a scatter up, in star formation rates that is actually quite significant, more than order of magnitude. And this is something the model doesn't match. So we realize that we actually need to add stochasticity to star formation to the model, because the framework, it's not surprising, because the framework was designed, the fiducial model was designed simply to model average star formation in the galaxy, whereas stochasticity and bursts of star formation in these galaxies are driven by formation of individual star-forming regions and their disruption, either by tidal forces or by feedback. But these individual star-forming regions, of high-resolution things within these galaxies that are not included in the model, are causing the bursts and causing the scatter in this relation. Fortunately, it's not that difficult to add such stochasticity. And we started doing this again last year, not for JWST data, but actually motivated by this plot and realization that we actually need to add additional stochasticity. We use the framework developed by Sandro Takela and collaborators for doing so, which simply adds stochasticity by perturbing the mean star formation rate by a random number, so 10 to the delta, where delta is a correlated Gaussian number, drawn with such that these numbers have power spectrum of particular type. It's a constant on longer time scales and then power law at short time scales. The motivation is arbitrary, but there is actually pretty significant motivation for using this form because it's very generic. It comes out from modeling of processes within the interstellar medium, formation and disruption of GMCs. Such models predict generically that there should be a power law on small scales. So large scales, the stochasticity is simply driven by stochasticity of the rate of accretion by the galaxy. To illustrate, here is an example. This is an individual galaxy, star formation rate as a function of time in the model. So this is just one galaxy. And the average star formation history predicted by the galaxy, which is barely seen here by dashed line, is kind of smooth. It varies. It follows the cosmological accretion, star formation, and outflow. So all the processes are included, but it's relatively smooth. When we add stochasticity on top of it at a particular level that's specified by these parameters, you can see that you add a lot of variation, right? You get a lot of stochasticity, and it's quite significant, but actually it's at the level that's expected in the state-of-the-art simulations of galaxy formation. So what you see here is the power spectrum of the average model here, shown by dashed line, then the power spectrum with added stochasticity. This is what this fluctuating thing is, by solid line. And the color lines, the thinner color lines are showing you power spectra from various simulations and semianalytic models. And you can see that if you add stochasticity at this level, you start matching simulations like FIRE2, which have a lot of stochasticity at small scales because they resolve those individual star-forming regions. This plot shows you power spectrum and star formation history over the entire evolution of galaxies from 0 to 13 billion years. We actually expect that at high redshift, when galaxies are growing very fast, the levels of stochasticity should be larger, and this is illustrated on the next slide, which shows a similar plot, but now focusing on the first giga-year of evolution. This is a model galaxy evolved up to redshift 5 or so, and these power spectra again showing what the power spectrum looks like in this model for this smooth line, for the dashed line, and for the perturbed line, stochastic star formation model shown by the solid line. You can see that these power spectra actually lie below the power spectra that come out from modern state-of-the-art simulations of galaxy formation at redshift above 5. In particular here, they use FIRE2 and a simulation by Massive Arricotti group, Garcia et al. 2023. So it's at the low level, but of course it's a model, so we can crank up this parameter. We can crank up normalization of the power spectrum, say by a factor of 2, then the model starts to lie somewhere close to where simulations indicate, and if we crank it even more, we can get to the upper limit. But even in this case, I would notice this number, 0.35. Even in this case, the power spectrum of this model, despite these huge fluctuations, stochasticity is still smaller than the smallest mass galaxies in the FIRE2 simulation, which only reach 10 to the 9 solar mass by redshift 5. The main point that I want you to get from this is that within these limits, so sigma delta, normalization of this power spectrum, 0.35, 0.15, they're perfectly in the range of where simulation suggests the stochasticity should be at the stellar masses that we're considering. There's also a trend, although it's kind of difficult to discern from all these various lines, there's a trend that the smallest galaxies exhibit the highest stochasticity. These galaxies have final masses reaches 5 of 10 to the 9, then there are galaxies of 10 to the 10, then galaxies of 10 to 11. So there is an increase of stochasticity as we go to smaller mass galaxies, and that actually also what we expect as we go up in redshifts, the average mass of a galaxy should get smaller and smaller, right? So we should expect that stochasticity should increase. What I'm going to do in the remainder of my time is I'm going to show you what effect it has on the UV luminosity function of galaxies. This slide first looks at UV luminosity function at low redshifts, redshifts below 10. This suddenly quickly becomes very mundane and relatively low. But what you can see here is observations. It's a combination of JWST and JWST, and the model predictions, where dashed lines show a model without any added stochasticity, just as it would come from fiducial model. Solid lines show when we add stochasticity at the level that at the low end of what we expect at those redshifts, as I said. You can see that, first of all, the stochasticity doesn't make a huge difference here at these redshifts, but with relatively small level, we can match observations. We actually could match it even with lower level if we reduce the depletion time of molecular hydrogen used in the model somewhat. So here, essentially, at these redshifts, there's no particularly strong indication or need for stochasticity, but it's probably there at some very low level and affects the shape of the luminosity functions a little bit. At higher redshifts, however, the same parameters do not work. This is something that was realized a year ago, and then people are struggling to understand what is it about. What you see here is UV luminosity function stretched at 11, 12, 13, 16, shown on the y-axis as a function of UV luminosity, and the predictions of the model without star formation stochasticity and width, shown by the solid line. You can see that it progressively underpredicts the measurements, and the difference starts to increase with increasing redshifts, right? And that's what generated headlines that Big Bang is in trouble, right? But now remember that this level of stochasticity, we generally expect the stochasticity increases with high redshifts. There is physics behind the simulations are showing this, and this value is at the low end, right? So what's going to happen if we crank it up? If we crank it up to something that's within the middle where simulation is suggesting, the UV luminosity function is matched, right? So this is, of course, you can say this is serious magic. Serious got the data and understand what needs to be done. But again, none of this. This model was designed for galaxies at redshift 0. So it reproduces properties of redshift 0 galaxies. The simulations that produce that level of stochasticity existed before just the JWST measurements. So there is really nothing new here. We're just putting it together to interpret the data. Now, there is a very distinct prediction also, not just to say that we're fitting the data. The model actually makes very definitive prediction that with increasing redshifts, the UV luminosity function should get flatter. And you can test this prediction with the future measurements. So given that I'm out of time, I'm going to end with my conclusions and just stress that there are predictions that this particular interpretation of high redshift UV luminosity function makes. And this is that UV luminosity function should get flatter, something I didn't show you because I don't have the time, but you can ask me afterwards. At the same time, the star formation rate stellar mass relation is also expected to get flatter with increasing redshift. So there are testable predictions that this interpretation makes. Thank you.
Any questions?
Yeah, next talk. I have a question like, do your model make any prediction of the central supermassive black hole properties, or whether you think the aging would influence the dwarf galaxy evolution? Something like that. Yeah, thank you.
So this model, thank you for your question. This model does not include AGN. It was specifically designed for modeling dwarf galaxies such as 0, so it purposely neglects anything that affects massive galaxies. So we don't include AGN.
In the back.
That's very interesting that you said your prediction is that at UV luminosity function is getting flatter at the brighter end. Can you say a little bit more about this? Because this is exactly what I showed previously, right? So at the very bright end, it's flatter, much flatter than lower redshift.
That's right. So until this morning, I thought this was prediction, but when I saw your measurements earlier this morning, I thought maybe this prediction has already been tested. So yeah, there is a very simple reason, because the underlying luminosity function gets, underlying stellar mass function gets actually steeper, but because of that scatter, when you get, if the scatter increases and the underlying stellar mass function gets steeper, the effect of stochasticity becomes larger, which flattens the luminosity function. So that's a very generic prediction of this interpretation. So there are other interpretations like changing the IMF of stars that people have discussed, but this specific interpretation doesn't actually require any new processes. It includes only galaxy formation processes that already were known prior to these JWST measurements. That interpretation makes this specific prediction. Yes.
Thank our speaker and all the speakers of this afternoon's session. Now time for the coffee break. We will start back at 3:30 on the dot, so make sure you're here in time.